So we're going to get started here by taking a look at what are we doing. We have, I hope some of you have been to our in-person star parties over the past few years, but tonight we have this really cool opportunity to share with you that our telescopes are being streamed through cameras on our roof deck, our observation deck. And so Tad right now is up on our roof deck, setting up the camera, and he'll be working it all from up there. Using a tablet and this interface that even controls the telescope mount, which is really, really cool. So it's kind of all integrated and allows us to see things that we can both see with our eyes, like the moon, but also some deep space objects that our eyes are a little hard to see with our eyes, because our eyes aren't quite sensitive enough that this camera will actually allow us to see. So, what we're going to do here is we're going to start by taking a look at the moon. So hopefully you can see it outside your window. Again, here at the museum, we have some southern-facing clouds. But our camera upstairs can capture these nice craters. And you might be asking, why are we seeing only part of the moon here? Well, during the first quarter or the third quarter phase, the moon is my favorite time to go look at it, because the moon's not washed out in its full moon phase. And you can start to see the craters along the terminator, that line that separates day from night. And you can start seeing some of those details. So you can see the shadows of the craters there, and really start to see some of the heights, those mountains surrounding those lower lying regions over on the left-hand side, called the Maria, or those basins that don't have quite as many craters. And one of the reasons why the moon is one of my favorite things to look at through a telescope is that a lot of us take it for granted, and sometimes I even do too, is that it can be out during the daytime, like it was this afternoon, and then it can be out at night, but it's such a wealth of visual interest that we forget about it since it's there quite frequently. So as we're looking at the picture we took last night through a camera as we're battling clouds up on the roof deck, are there any questions about the moon or what you've seen in the sky yourself? Okay. Well, close to the moon tonight, and I'll hold up my star map here, because the moon moves quite frequently from one day to the next. But if you look at your star map, down in the southern part of our star map, you can see the planets Jupiter and Saturn. And maybe you've seen these two bright objects in the southern sky and weren't quite sure what they were. They're some of the first things that come out at night when the sun sets. It's one of the first things that are quite visible before the rest of the stars become visible. So they're right there next to the moon tonight. So if those southern clouds do blow away as we're going here tonight, we'll get a nice clear shot of that. But I did see a question or a hand raised. If you go ahead and just enter your question into the chat, we'll go ahead and see what you have to say, or see what you've seen, or and we'll use the chat here today. So Sophia from Woodbury would like to know if the planets are close to the moon. So as we are looking out at the sky tonight, or yesterday, or tomorrow, they're going to look like they're really close to the moon. They're going to be two really bright points of light right next to the moon. Now, the moon moves quite a bit from night to night, so that's not going to be true next week. And when we're in outer space for real, the moon is nowhere close to Jupiter or Saturn. It just looks like they're in the same part of the sky as we're seeing it right now in these past few days here. What is the biggest peak on the moon? Know what? I'm not quite sure what the tallest mountain on the moon is. There are quite a few of them, and we can actually see one of those central mountain peaks here in this crater, kind of in the center of this image here. And so sometimes when our asteroids or meteors from outer space come and crash into the moon, they come in with such force that not only are they making that impression, but then it causes an upwelling in that center. So it pushes things in, but then there's so much energy that it pushes it back up and creates that kind of southern peak. And so there are several craters that have this high central peak here. There's one there in this image, And if we look just over here, there's another kind of smaller central peak there. And you can kind of see one over, sort of like looking like a hill in this particular image from last night. So I'm not quite sure what the tallest one is, but somebody would know. I just don't know that off the top of my head, but good question. A few other questions coming in are, why do we only see one side of the moon? And what do we know about the dark side of the moon? Well, we only see one side of the moon here because the moon is rotating on its axis at the same rate it orbits the Earth. And so as this happens, we call it tidally locked with the Earth. So we only see the near side of the moon. And of course, we can really only see the near side when the sunlight's reflecting off of it. So that back side of the moon that we don't see, or that never faces the Earth, we've nicknamed that as the dark side because we don't get to see it from here on Earth. But actually, that gets just as much sunlight as the near side does. So all sides of the moon get about 2 weeks of sunlight during the month and then 2 weeks of darkness during the month. So there really is no dark side of the moon. It's just the far side that we can't see from Earth because the moon's rotation is tidally locked with its orbit around Earth. But that's kind of a fun question. It's not the only moon that's tidally locked there. Another question came in is there a good way to help me and my students remember when the moon is waxing versus waning? Yes. And all you need are your hands. So if you make you're going to see it backwards for me, but if you make the lowercase b with your left hand here, the curve of your hand versus the straight stick of that b, if the curve of the moon is on the right side of the moon, like a lowercase b, we know the moon is being born, or it's waxing, it's getting bigger, or it appears to be getting bigger, I should say. However, if you make that same shape with your right hand, you get a lowercase d. So if you see the moon and that curve of the moon is on the left side, then the moon is dying or waning. So it's not actually dying or being born. It just, from our point of view, we see more of the sunlit side or less of the sunlit side. And so that's a quick trick that I like to use, is just my hands. Does it look like the curve is on the left side or the right side like a lowercase b, or does it look like it's on the left side like a lowercase d? And then I can tell if it's waxing or waning. So that's what I like to use. Okay. How do we know where the moon is going to be in the sky? It's going to change quite a bit from one night to the next. So if we're in the full moon phase, the moon is going to be opposite the sun. So that means when the sun is setting, the moon is rising. And when the moon rises, when the sun rises, the moon's going to set. And so it depends on what phase it is. Full moon is always going to be opposite the sun. Now, a crescent moon, which is going to be close to a new moon phase, that's going to be really close to the sun. So it'll rise with the sun or set with the sun, fairly close to those times. So it depends on what phase it's in. If it's near the new moon phase or further or near the full moon phase, it'll be either with or near the sun or directly opposite the sun. Okay, got a question from Cliff asking, what is the deepest crater on the moon? That kind of goes with the tallest mountain on the moon. You know what? I'm not quite sure. That is a fact that escapes me. That's a great question, because as we're looking at the picture of the moon that we took last night, that we see that some of these craters are quite deep. And then we even get some kind of mountains or valley ridges here. And so I just don't remember the topography of the moon enough. I am not a geologist, but those are great questions. And if you find the answers, I would love to know, because I just don't remember them off the top of my head. Okay, I see one here from a Jazzy. What composition is lunar soil? Lunar soil is much like our Earth soil. And that was one of the surprising things that the Apollo astronauts found when they brought back samples from the moon, is that it has the same amount, it has the same stuff in it. It has quartz, and it has olivine, which is kind of a fun green colored rock, kind of looks like a green olive. So that's how I think they got the name olivine. And so it's only by really studying them with a microscope and some lab equipment that we really can tell if a rock came from Earth or came from the moon, because the rocks can be very, very similar, that we actually have to get down into those lab equipment type studies to tell where did a rock actually originate. And a lot of that goes to support the idea that the moon used to be part of the Earth. So that a long time ago, something very large came and hit the Earth back when it was still forming, and a chunk of it got ripped off, and that reformed together and coalesced into the moon as we know it today. And so the moon composition is very, very similar to Earth's. One of the surprising things the Apollo astronauts found on the moon was this orange soil, these little orange glass beads they found. And that actually has to do with volcanic eruptions on the moon. And so if we're looking at this picture of the moon here, we see over to the left kind of this larger dark area. These are the Maria, kind of big, huge basalt flats, or big dried up oceans of lava, if you will. Well, as the moon cooled down and as a new incoming meteor came in, it would kind of crack the surface of the moon, and molten lava would come out and spray into the air kind of like a jet. And when it hit outer space, it would instantly kind of crystallize in these little glass orange beads. And so that was one of the cool, surprising things the astronauts found on the moon, is evidence of past geological activity. Okay, so how big is the moon? That is a great question. The moon is about the same size as the entire United States. So it's about a quarter the size of the Earth, if you will. So it is fairly small compared to the Earth, but it's actually one of the larger planet-to-moon ratios out there. So there's plenty of moons out there, but we have the largest ratio between the size of the Earth and the size of the moon. Other planets like Jupiter and Saturn, they're just so massive and so large in size that even some of their largest moons are so tiny in comparison to their parent planet. So the moon is about a quarter the size of the Earth. Great question.
Hey, Sarah.
Yes.
Hey, I'm going to jump in, and I'm going to share my screen if you don't mind.
Okay. So Tad's up there with the telescope, so he's going to jump in and share some stuff with us.
Hi, everyone. So the voice just popping in here. Tad, I'm the planetary educator. I'm up on our deck with our telescope, along with Darcy. I don't know if you can see. Darcy's over there. Darcy's one of our student staff. And we've got our moon here. And I just wanted to give you all a live view while we still have it. I'll see if I can make it a little bit brighter as well. We're fighting the clouds, so I wanted to make sure you all got a chance to see the moon here. You can't see it from where we are. We've got some clouds, we've got some haze. But Sarah, if you want to, I'll hand it back to you. Just want to give you a live view of the moon.
Okay. And so, yeah, that's one of the things. The astronomy is great, but we never know what the weather is going to do. It could be clear one moment, and it can be cloudy the next. And so as we're looking at the moon here, we can see that it's upside down from what I described, because we're looking outside in real life. It is the first quarter phase, or near the first quarter moon. But here in the live share, it looks upside down. It almost looks like the third quarter phase. And that has to do with how telescopes are. And here Tad's going to kind of swivel our eyepieces and our cameras around to give us a little bit more true view of it, of what you'd look outside if you're just looking with your eyes. And so there you can kind of put that practice of using your hands to either make a B or a D. In this case, we see that terminator line that kind of comes straight down, separating day from night. And the curve is on the right side of that, kind of like the lowercase b. So we know the moon is being born. It's waxing. It's going to get larger. And we can see some clouds rolling in as our image kind of dims down a little bit there. But that is kind of the fun and exciting nature of astronomy. It definitely keeps us on our toes. Okay. Let's see. So we have a few more questions coming in about the moon here as we're looking at the live shot. How does the moon affect ocean tides? Well, everything in the universe has gravity. The Earth has gravity, the sun has gravity, you and I have gravity. Except for you and I, us human beings, are so small, the gravity that we have is so little that we can't really feel it. But the moon is actually pulling on the Earth as well. And so it's that interaction between the moon and the Earth and the gravity that pulls on the oceans, and kind of the force is pulling it. And so that's why you get a high tide towards the moon, but also on the direct opposite side. So that's why you have high tides and low tides on each side of the Earth. So it's the gravity and the balance of the forces as the moon also pulls on the Earth, as the Earth pulls on the moon to keep it in orbit around us, that cause our tides. And then it looks like there's another question. Are there mountains on the moon? Yes, there are mountains on the moon. So in our live telescope view here, again, it's a little hazy, but if you look up towards the top of the image, there's some craters there. The crater walls will actually cause some mountains, but then also along some of the ridges of kind of in the middle of the moon as we're looking at it, has those those dark gray patches. Those basins will have some mountain ridges along the edges there, separating kind of those dark gray patches from the lighter areas of the moon called the highlands. And the highlands are where you can find way more mountainous regions. And they're also going to be older rocks. Those lower lying darker areas, those Maria, are going to be fairly new land. And we're talking new as in a couple of million years old, because a lot of things in outer space are fairly young. Even when we say they're just a million years old, that's still really fairly young as far as outer space ages go. But there's plenty of mountains on the moon. Okay. Got another question about what size is the moon? The moon is about a quarter the size of the Earth. So about the United States, if you look at a map, moon from side to side is only going to be about the size of the United States. So it's quite large as a ratio of moon to planet, but it is still smaller than us. Okay, so what would happen if someone tried to dig into the moon? Well, the Apollo astronauts did take rock samples from the moon. So we took a lot of surface samples. I don't remember how far down they drilled, but I know they took samples at the moon. And the moon has gravity. It's just not as much as Earth does. And its rocks are very similar to the Earth. And it has cooled down all the way, so there's no more active volcanoes or kind of lava hiding at the core of the moon. And so we wouldn't expect anything disastrous to happen if we went there and drilled down even further than we have before. But humans have not been back to the moon in almost 50 years. Apollo 17 was the last time humans were on the moon. And so those are the last rock samples that we've collected, and we're still analyzing them today. Okay, so I think we can totally come back to more questions about the moon, and we'll still enjoy some of the shots here that are coming off our roof deck. But we have some other cool things to show you that are in the sky. And so for this one, what I want you to do, if you happen to have your star map, kind of grab that. What I can do is I can drop that link back into the chat. So if you were with us from the beginning, you can grab that, or I'll grab this back down here and put it in the chat, and you can follow along with us with your own star map. We're using the September-October one, but our past ones are on there as well. Now, we all live here on Earth, and Earth is in the solar system, and the solar system is in the Milky Way galaxy. If you happen to live somewhere where it's dark enough and you're away from city lights, you might actually get to see that Milky Way stretching across our night sky. Now, here in the Twin Cities in Minnesota, we have way too many lights to actually see that with our eyes. But there's another galaxy out that's nice and high in the sky this fall. Does anybody happen to know what galaxy I'm referring to? Okay. It is the Andromeda Galaxy. And so I'm gonna go here and share my screen yet again. And we'll take a look at the Andromeda Galaxy as seen through our telescope this past week. It's hiding behind the clouds at the very moment. But we're gonna go ahead and do that. Okay, so here we have the Andromeda Galaxy as seen from our roof deck here this week. Now you may have seen gorgeous colored images of the Andromeda Galaxy. It's one of the things that's best viewed or most photographed. And here we're seeing a very small part of it because our camera is being sensitive to all the pixels on the camera, and so it's picking up all the black and white, all the energy from it. And we didn't put colored filters in. So when you see pictures from the Hubble Space Telescope, they can be colored to highlight different areas of the galaxy or highlight different areas of a nebula. But in this case, we're seeing the Andromeda Galaxy as our eye would see it, because the Andromeda Galaxy is so far away from us that our eyes can't detect color coming from this galaxy. Now, what we can see here, and what's really interesting to see, is that it's near the constellation of Cassiopeia. It's actually in the constellation of Andromeda. So if you have your star map again, look over towards the east. Here, and I'll hold mine up again. So we're looking over towards the east here. And right above Mars, so there's Mars coming up above the horizon, you'll see these 4 dots, which are the Great Square of Pegasus. And then right off of Pegasus is Andromeda, and hiding right off the side of the stars of Andromeda is the Andromeda Galaxy. The Andromeda Galaxy is actually one of the things that told us that we weren't it. The Milky Way was not the entire universe. And so when we first saw this hazy smudge in our sky over in the Andromeda constellation near Cassiopeia, which looks like a W of stars, check out our latest Constellation Hunter video if you want to figure out where Cassiopeia is and how to find that. That just came out this week. This little fuzzy patch that we're looking at here on the screen, Edwin Hubble, the astronomer, he pointed his telescope at this and he measured the distance to these stars. And at the time, we thought that the Milky Way was it, that everything we saw in the sky was all in the Milky Way, just different neighborhoods. Like we're one neighborhood here in the solar system, and that the other stars we saw were just kind of our neighbors across the way. But Edwin Hubble was able to use calculations in his telescope to find out how far these stars were. And when he did that, his numbers were so large, he knew they were beyond the size that we had calculated the Milky Way galaxy to be. So this galaxy was actually some of the first observational evidence and data that we are not the only ones out here. The Milky Way was not the entire universe. And this discovery happened just about 100 years ago in the 1920s. So we have known about the entire universe beyond our own Milky Way for less than 100 years, which is kind of mind-boggling thinking about how much we know about it today. But it was less than 100 years ago, or just about 100 years ago, that we even realized we weren't it. Okay, so a few more questions come in. Let's see what they are. What are the different kinds of stars? Okay, stars are one of my favorite things to talk about because they have such varied lives. So we have average temperature, medium-sized stars like our sun. So our sun is a nice yellow star. And then we can also have stars that are much hotter, that burn through their fuel much quicker and much hotter than our sun, in which case we'll get blue stars. Some of them are so huge, we call them blue giants. On the other hand, as stars age and cool down, they use up their fuel. And as they cool down, they'll go from being really hot and bright blue at their hottest, and then kind of cool down to middle temperature stars like a yellow sun like ours. And then when they continue to cool down and use up all their fuel, they'll kind of turn reddish. And they'll kind of swell up a little bit like a balloon. And so we'd call those red giants. And so those are just some of the stops along a typical star lifespan. But some of the stars here in the Andromeda Galaxy that Edwin Hubble used are called Cepheid variables, because stars aren't like a light bulb. You turn it on and it just shines with the same energy from it the entire time. Stars can vary in their brightness and their energy output. Sometimes it's because they're physically swelling and shrinking, and other times it could be because something's going around them and eclipsing them, so they seem to kind of blink or twinkle at us. Looks like Tad has something to add in.
Yeah, sorry, I'm not laughing. I'm laughing because Darcy is now holding the tablet up to give me a little bit of light on my face. Thank you, Darcy. But staying 6 feet away. Sorry. So we've got a dead star if you'd like to see one.
A dead star? Sure, yeah. Let's talk about a dead star.
Perfect moment here. I'm going to share the screen on my tablet here. Let's make sure. Get it right. Whoops. Well, that's the tablet itself. Oh, look at that. All right. So it is a little out of frame there, I realize, but looking near this top center, little overexposed for because there's a lot of clouds going over, but we should be able to keep an eye on M57 there. But I'll let you take it away again with M57.
Okay, thank you. So here is an example of a dead star. And so if we look here at the screen that we're seeing through our telescopes, we see this kind of ring that Tad was talking about. So we do call this the ring nebula. And so I was just saying that stars can live their lives and they use up their fuel. And then once they completely use up their fuel, depending on the star and how big it is, it can actually die in a few different ways. So our sun is a medium-sized star. It's not big enough, and our sun will never explode and will never turn into a black hole. In order to explode and turn into a supernova and maybe even possibly a black hole, you have to be 8+ times the size of our sun. Now, our sun, when it dies, what's going to happen is it's going to cool down. It's going to use up some of its fuel. It's going to swell up, kind of like a giant balloon, and it's going to puff out its outer layers. And what's left eventually will be the core of the sun, kind of like an apple core, if you will. And this is what we're looking at of a star that died in a very similar process that we expect our sun to die in 5 billion years from now. So we don't have to worry about the sun dying anytime soon, but in 5 billion years, our sun is going to turn into something like this. This is called a planetary nebula. When a star that's of medium size swells up, poofs out its outer layers, and at the very core will be a white dwarf. The sun, when it turns, when it kind of does this process and poofs out its outer layers and leaves just the core behind, that core will be roughly the size of the Earth. So if you know how much bigger the sun is compared to the Earth now, the core of the sun will be much, much smaller when this happens in billions of years from now. So what we're looking at here is the Ring Nebula. It is in the constellation of Lyra, the Lyre. So again, if you have your star map, look towards really close to the center. And what we'll see here, very close to the center, is M57. It's this ring nebula just off of Lyra. And Lyra is one of the 3 constellations that are connected by the summer triangle. So if you're familiar with the summer triangle, it has Deneb in one corner, it has Vega in the other top corner, and the southern tip of the summer triangle is Altair. And so Vega will be that bright star that's closest to M57, and it'll be just south of that bright star Vega is this ring nebula. The Ring Nebula is kind of faint, so you're not going to see it with your eyes. So you would need a backyard telescope in order to start seeing this deep space object, which is one of the great things about being able to live stream to you guys here now with our cameras. They can take pictures for longer exposures than what our eyes can see. And so we're actually seeing stuff that you may not be able to see if you were to come here on an in-person event in the future. But there's still lots of cool stuff that I highly encourage you to look through the telescope yourself. But this is some of the really cool, exciting things we're able to bring you now here virtually. If you were to look at a Hubble Space Telescope image of this Ring Nebula, you'd start to see colors. Again, this is what our eyes would see if we could keep them open long enough to start collecting this light through a telescope. But at the very center, you can would be the leftovers of the star, that white dwarf star, that dead star. But then that ring we're seeing here is its layers puffed out, and those layers give off different colors of light. And so by looking at the different colors of light that are coming through those layers that are puffed out of this planetary nebula, we can see that this nebula has some hydrogen and helium, like most stars do. But then it also has some nitrogen and some sulfur in it as well. And so by looking at the colors that are getting kind of expelled from this dying star or this dead star, we can tell what the star was made of. Okay. A few more questions came in. How long do stars live for? This is from Catherine. Stars live for different lengths of time depending on how big they are and how fast they burn through their fuel. So in a case like our sun, it's a medium-sized star, it's a medium-temperature star. Our sun will live for about 10 billion years. Now, stars that are much larger than the sun, because they're much larger, they burn through their fuel much quicker. Kind of if you think of a car, a sedan, compared to an SUV. An SUV is much larger. It takes more energy to keep it going and driving down the road. And so it's going to burn through its fuel a lot faster. But then there are also stars that are much smaller than our sun that are cooler as well. So that'd be like comparing your sedan car to a hybrid or an electric car. It can burn through its fuel a lot slower and go the same distance. So smaller, cooler stars will actually live a lot longer than your really big, massive, hot stars. It's just because they'll consume their fuel at different rates. And so there is no typical lifespan of a star saying all stars will live 5 billion years or so, but we have been able to categorize them into what's called an HR diagram. And so that's how we can kind of see these patterns of large hot stars living shorter lives than the smaller, cooler stars living much longer lives. And so there's ways we can take these observations and organize them to kind of predict how long stars will live for based on their size and their temperatures. That's a great question. It's one of my favorite things to talk about is star lifespans. Okay, is it a brown dwarf star? I'm hoping that is, I'm thinking that's in reference to the telescope you were looking here at through the, at the Ring Nebula here. At the core of the Ring Nebula is a white dwarf. So a white dwarf is kind of the opposite of a brown dwarf star. A white dwarf is the death of the star. It's the leftovers after the star has died, after it's stopped making its own energy. A brown dwarf is a star that wasn't quite. It means it was in the process of gathering material early on in this formation and started gathering enough stuff and got big, but not quite hot enough to ignite and to start the process of fusion that has that gives stars their energy and their light and their heat. So brown dwarf is kind of like a failed star, if you will. It's almost exactly opposite of white dwarf, but they're both still fairly small. The Helix Nebula is also another example of a planetary nebula as well, yes. So as stars die, what's interesting about this one here, the Ring Nebula, is that it kind of expelled its gas in this ring. It's not quite symmetrical. If you look at it, it's almost elongated, a little bit more football shape, if you will. But planetary nebulas, when a star finally just sheds those outer layers and expels them into space, they can be many different designs, if you will, because based on the star's magnetic field, that gas will escape in different patterns. A really cool one is the Ant Nebula, where it kind of spread it out on both sides. And so it's long, kind of like the, I'm not an entomologist, so excuse me if you know more about insects than I do, the thorax of a insect. And sometimes they expel out kind of like butterfly wings, or one of them even looks like an owl's face. And so planetary nebulas can have many different views, and they're gorgeous, many different shapes, all based on how that star expelled its outer layers of gas.
Sarah, can I interrupt again?
Go for it.
Does anyone out there like Jupiter?
I think we all love Jupiter.
Okay. You know what? I think we've got it. Give me a second here. This is coming through a different camera, so it's going to be a little bit different look. It's going to be a little bit greenish. I think some of our pixels are a little messed up on this camera. But we have got in front of us, hopefully you can pick it out. Well,
yep, I see it there.
All right, I'm going to hand it back to you.
Okay, so it looks like the clouds in the south cleared up just enough where Tad was able to see Jupiter through our telescopes. And as we're looking at this is a slightly different camera, and you can actually tell some of the stripes on Jupiter. So if you look here kind of in the middle, they're not super distinct, but you can see there's kind of a darker stripe and then some lighter stripes and another very thin, darker stripe towards the top, and then it almost looks like the cap of the planet is a bit darker. And so these are the wind patterns and kind of the different stripes you would see on Jupiter as if you were to look at through the Hubble Space Telescope. And that's one of the awesome things about looking at these planets is you don't need something that's huge and powerful like the Hubble to see great detail just here in the cities looking outside your house or your yard. And looking at Jupiter actually helped put into context where Earth was in our solar system. So in this, we can't quite see it because we don't want to overexpose it for you, and the clouds might be blocking it as well, is Galileo. When he first looked at Jupiter here with his very rudimentary telescope back in the early 1600s, he saw these little specks orbiting around it. And that was really quite revolutionary because at the time, we thought the Earth was the center of our solar system and that everything had to orbit around us because obviously we see the sun rise in the east and setting in the west every night, the moon rise in the east and sets in the west. So everybody was convinced that the Earth was the center of the solar system. And at the time, that's what we considered the universe. But when Galileo first looked at Jupiter, much like we're looking at it right now, he saw little tiny specks orbiting around it. And these moons, these 4 large moons that Galileo saw, proved, well, it gave strong evidence for, and now we know, showed that the Earth was not the center of the solar system, that something else out there could orbit a body that wasn't the Earth. And so Jupiter was some of the first evidence putting our solar system into the organization we now know it is, with the sun in the center and the planets orbiting around it. And so I always find it really exciting looking at Jupiter outside because I feel like I can make those same observations Galileo first saw and really be a part of the history of astronomy and our understanding of where we are in outer space. And so I love looking at Jupiter through a telescope. Okay, let's check the questions. I see a lot of them coming in. Is Jupiter a failed star? Some people like to refer to Jupiter as a failed star. It's not quite big enough to be a brown dwarf or officially a failed star, but it's not too far away as far as we're talking about from being that. So it very well could have, if it was given enough time and enough material to gather and make itself larger, eventually it maybe could have become a star. But Jupiter itself is not big enough, so it is not a failed star. And the fact that it's moving around the sun is one of the definitions of what a planet needs to do, is orbit a star like our sun. What are the specks made out of? I see that here from Brian. So the specks I was talking about before would just show up in our camera here or in that first telescope of Galileo's as little tiny dots on either side of the planet. And those are actually the moons of Jupiter. Jupiter has 79 moons total that we now know of today, but you can see 4 of them through a strong pair of binoculars or a backyard telescope. And it looks like TAD's increasing the exposure length of our telescope here. And so if you look off just to the left of Jupiter, and then you see 2 more a little bit further away, those specks, those are those moons that Galileo first saw that gave observational evidence that the Earth was not the center of the solar system. And so those are really exciting, I think, to see, because again, that's what makes me feel like I'm participating in the history of astronomy.
And just to be clear, if you're seeing a lot of other red and blue and green pixels, that's a lot of hot pixels. So they're those pixels that are overexposed in the camera. And that's not actually in space. That's just bad data, which is why you spend a lot of time taking good data to make up for all the bad data.
Yes, so because Jupiter is so much larger, it can reflect a lot more sunlight back to us than its moons. And so in order to see the moons like we're seeing now through the camera, we have to overexpose or get too much light coming off of Jupiter to even see the moons orbiting around it. So then those colorful specks, the red, the blues, and the greens around it, that's just our camera. Those are artifacts of having to be tuned up so high to overexpose Jupiter to see the moons coming out. Okay. So, how big is Jupiter? Okay, the best way I know how to explain this is think of like your gym class with a whole bunch of different size athletic balls. So if you had a huge one that was 16 inches in diameter, that would be the sun. So this here is roughly the size of the sun. Now, if you had a golf ball, that would be the size of Jupiter. And then compare that to Earth. If we were to get a pin, like at the end of a push pin that you'd put in your corkboard, that little tiny end of it, that would be the size of Earth. And so if the sun is a giant kickball about 16 inches in diameter, Jupiter is the size of a golf ball, Earth is the head of a tiny itsy-bitsy pin. So Jupiter is much, much bigger than Earth. So are those small spots to the lower right moons? So as we're looking at Jupiter here, the 3 moons that I'm able to pick out on the image are to the left. They look like little green dots to the left, kind of towards down, if you imagine the face of a clock, maybe a little bit towards 8 o'clock or 7 o'clock on your clock face there. So those are the moons. And you can track them from night to night, because just the other night, one of them was on the right-hand side of Jupiter here. And so they do orbit Jupiter at fairly quick speeds. Why is Jupiter so big? Great question. If you think of our solar system is kind of organized where we have our rocky planets that are smaller towards the center of our solar system, kind of closer to the sun, and then our larger gas giants further out. And so there's that line between where we have our rocky planets and our gas giant planets. We have the asteroid belt. Now, the solar nebula theory of how planets formed, or how our solar system formed, is that the lighter materials like hydrogen and helium, those gases, it was too hot at the center of the solar system for those gases to collect. So they kind of got pushed out to the outer edges after the sun was formed, because the sun formed first. So then the heavier things like iron and rock, they were able to stay in kind of their solid form. They didn't get evaporated away. And so that's why the inner planets are made out of rocks. They're the heavier things that were able to stay in kind of more solid form at such high temperatures close to the sun. But those lighter elements like helium and hydrogen and sulfur and ammonia and all that stuff kind of got pushed out to the outer edges of our solar system, where it was cool enough where they could condense. Now Jupiter and Saturn and those gas giants have a lot of those really light gases on them. So they have combinations like ammonia and other things like that, but they also have hydrogen and helium. And so being that far out, they were able to start gathering all that extra material, and they gathered it quite quickly. And so Jupiter was probably one of the first things that started to form after the sun. And because it's been around for so long, it gathered more stuff very quickly and was able to become the largest planet in our solar system. So kind of, if you think of a big, huge craft table with a whole bunch of supplies just covering it, and you give one person a head start to collect as much stuff as they can, and then you tell everybody else to start, that was kind of like Jupiter. It got a head start, it collected as much as it could, and so it got very large very, very quickly. Okay, what are the names of the moons of Jupiter? So Jupiter has 79 moons. But the ones that we can see here and the ones that Galileo saw are the 4 Galilean moons. They are called Io, Europa, Ganymede, and Callisto. I remember them, and those are the orders of their orbits as you're getting closest to Jupiter to farthest away of those 4. You can remember them by I eat green carrots. So Io, Europa, Ganymede, and Callisto. So those are the 4 moons that you can see with a strong pair of binoculars or a telescope in your backyard.
All right, Sarah, I'm back.
You're back. What do you have for us?
Well, let me see if I can get out first here. We're going to go back to our other camera. And
ooh,
what do you think that is?
That looks like a globular cluster to me.
It does. It's a little fuzzy. Our focus is a little off here, and we've got a little bit of wind and clouds. But we're getting a pretty good view, and we're stacking some more images as we go, so make it a little better. Well, it's just the best globular cluster. There's no other way to put it.
So is this M13?
It is indeed, yes.
Okay, so M13
back to you.
Is a staff favorite of ours. That is the globular cluster in Hercules. And so if we go back to your star map, what we're going to do is we're going to look a little bit more towards the west now, just west of Lyra. Still kind of straight west, and Hercules kind of has his limbs going all over the place. It almost looks like he's doing a cartwheel. But so if I hold it up here, and so Hercules there looks like he's doing an upside down cartwheel. You have his head, and then his arms and his legs kind of coming out here, and then just off to the side, that's where M13 is. And this is something that's about a magnitude 6. It means you have to get outside the city lights, outside the light pollution, and you could probably see it with a pair of binoculars here. But it's really easy to find with a pair of binoculars or with a telescope, and it's gorgeous. What we're looking at are hundreds of stars. Now, globular clusters, these stars were all born roughly at the same time, and so it was like a big, huge, dense cloud of gas and dust. And in this nebula, these stars started forming, and it formed a whole bunch of them. And they're all kind of really tightly clustered here together. So as we're looking at this, we can see a tight cluster kind of towards the middle of this image. And then as the stars kind of get out a little bit further, their density drops down a little bit. But globular clusters are exciting because they are kind of in this region of our galaxy, kind of hanging outside in a halo above and below the Milky Way and in other galaxies as well. And so what that tells us is these stars are going to be some of the oldest stars that are out there. Some globular clusters of stars are estimated to be at nearly 12 billion years old. And the universe itself is only about 13.8 billion years old. So some of these stars are some of the very first stars ever formed, and they kind of hang out on the edges or the halo around a galaxy, which tells us they probably formed along with the galaxy before the galaxy ended up taking its shape. And so the globular cluster here is like a treasure trove of stars, all tightly packed here. And each speck here we're looking at is its own star. Some of them are going to be are hotter, and some of them are going to be cooler. So we talked about how stars can have different lengths of lives. Now, all these stars can be born roughly at the same time, or have formed roughly at the same time, I should say. But they're all different sizes, different temperatures, so they will not all live the same length of a life. And so if we were to put colored filters over here, or if you see it in a telescope like Hubble, you might be able to start seeing those yellows and those blues and those red stars. It tells they're different temperatures, which tells they're going to live for different lengths of time.
Hey, Sarah.
Yes.
I know we just got to M13, but it's clear to the south. So I want to share something else.
Okay.
Because that image is being stacked, so we got it here.
Yep.
This one is probably going to delight a few people out there.
Ooh. And so this is Tad's favorite. This is Saturn. And this is just that other bright speck next to the moon tonight. So we'll have the moon in the south, and then the brightest speck next to it just off to the east is Jupiter. And then ever so slightly more towards the east, slightly dimmer than Jupiter, is Saturn here. And you can actually see these rings, which are Tad's favorite. It's one of our staff favorites as well. Like Jupiter, this is one of the things that Galileo saw that gave evidence of what the solar system was like way back in the 1600s when the telescope was first invented. Galileo, when he looked at this planet, he didn't know what he was seeing because he saw the planet in the center, but he saw these things that going off to either side. And so he called it a planet with ears. We now know those ears are actually the rings of Saturn, and here we can see enough detail where we can see the gaps between the rings on either side and the planet itself. So while all gas giants, Jupiter, Saturn, Uranus, and Neptune, while they all do have rings, Saturn's here are the most abundant, and they have the most ice content in them. So they reflect sunlight very, very well. When we were at Jupiter not too long ago, we didn't see its rings because Jupiter's rings are very thin and very dark, and they don't have a lot of ice content, so they don't reflect light very well. But Saturn's here are gorgeous, and you can see them this far away, even from here on Earth. I'm seeing a question come in. We have that beautiful picture of M13, that globular cluster we're just looking at. What is the telescope mirror diameter that was used? So that particular one was taken through our Celestron 9.25-inch telescope. Here at the museum, we have several different diameter telescopes, and the telescope diameter is actually what tells us how much light it can collect. So it doesn't matter how long or big it is in that case, it just matters how big is that diameter of that mirror or that lens, and that's how much light it can collect, and that's what allows us to see some of these deep space objects.
And I just wanted to jump in and say that's 235 millimeters if you're using civilized units.
Yes. So Lainey from Minneapolis is asking, are stars alive? So that depends on how you want to define life, because stars definitely do have a life cycle. And so they are formed, they live their lives, they burn up their fuel, they do evolve. They take hydrogen and turn it into helium and turn it into carbon and oxygen. And when they do die, when they stop nuclear fusion, we call it the death of the star. Some of them are big enough where they explode out completely, like a supernova, or some of them are not quite big enough, they just kind of poof out their layers like that Planetary Nebula, the ring nebula we saw a little while ago. And so you can track the lifespan of a star and the cycle of a star. But really, if you want to get into it, astronomers, we do say that stars are alive. They have their lifespans. We talk about them. kind of in that personal tone. But then you might have an argument with a biologist if you want to get to the nitty-gritty of it. But yes, stars do have lifespans. They do form and they are born and they do end up dying. So astronomers, we like to say they are alive, yes. What are the rings of Saturn made out of? Most of the rings here are going to be chunks of rock and ice. Now, we don't fully understand why some planets have rings and some don't, or how those rings got there. What we are able to study here on Saturn's rings, we had the mission Cassini orbiting around Saturn for many years. And one of the things that that particular orbiter found is that some of the inner rings and those inner chunks of rock and ice were actually falling into Saturn, kind of like ring rain. So raining down on Saturn. So these rings might be temporary. But again, when we're talking about lifespans in space of objects like planets and stars, temporary is close to millions of years, because planets are around, our planets are about 4.5 billion years old. Our sun is 5 billion years old. Stars can live for much longer than that. So these rings around Saturn might be disappearing in the next few million years. But from what we've been able to find out, they could potentially have been a moon that was close to Saturn that got ripped apart into these tiny pieces, or they could have been material that never was allowed to form a moon to begin with. And so the rings, we don't fully understand why planets have them or where they originate, but that's one of the questions we're currently investigating. How long till Saturn's rings disappear? We're estimating a few million years. Yep. So again, that's a quick, short period of time as far as outer space goes, but much longer than our human lifespans. What is the magnification of the telescope? Well, telescope magnifications depend on the diameter of its primary mirror or lens, and then whatever eyepiece you put in it. So you can actually change the magnification of a telescope just by what eyepiece you're putting in it. So we just think of telescopes as big light collectors, kind of like a big bucket collecting light. And then we can change magnification by what eyepiece we have. And so I don't remember exactly with our cameras up there what magnification that combination has for us tonight. But know what? I can write that down and I'll see if I can get back to you in the comments later on. I'm going to write that one down. How many ring particles does Saturn have? We don't count because most of those particles are fairly small. They're going to be about the size of the end of your pinky here, or dust under your bed, to maybe about the size of a small basketball. Most of them aren't going to be very large. There's nothing that we can land on or walk across. And so it really doesn't make much sense to count them as individual particles. We do group them together by where they are in orbit around Saturn, because you'll have a ring and then you'll have a gap where there's nothing. Or maybe there's a moon, one of Saturn's shepherd moons that collect material and push it back into the rings. And then you'll have another wide ring. And so we label those rings with letters A through, I think we're all the way up to F. And so we don't count the individual specks, and they're not solid and they're not continuous. So we just count the bands based on where the gaps in the rings are. Yep. How big is Saturn compared to Earth? Now, this is the number I always forget, but I'm going to turn this over to Tad if he can hear me, because Saturn is his favorite planet. I can't remember if it's 21 Earths across or if it's 12. Tad, can you jump in?
Sorry, what's up?
How big is Saturn compared to Earth?
Yeah, so if you look at the rings here, that's about 21 Earths from one edge to the other. So Saturn itself is about 9 times the size of the Earth. And a good way to remember this, the way I always remember it, is actually in miles, in freedom units. And that's about 180,000 miles across. And 180,000 miles across, some of you already know where I'm going with this, 180,000 miles across is about 1 light second in diameter. So light travels at 186,000 miles per second. So it takes about almost 1 second, or it takes a little under 1 second to go like straight across. Of course, light can't go straight across Saturn because the Saturn's in the way, but we'll ignore that.
So there you go. So it is 21 Earths would fit across from one edge to the other edge of the ring system, but about 9 across, 9 times the size of Earth is the size of Saturn itself. Yep. Okay, So I see a question coming in here. Why are Saturn's rings disappearing? Well, it has to do with gravity. And so the rings that are closest to Saturn, gravity pulls on things, and it's pulling those inner particles of rings into the planet. And so it's kind of like a shooting star, a piece of rock in outer space that comes through our atmosphere. We call a shooting star. It's just a rock from outer space falling to the Earth. Same thing with Saturn's rings. Saturn has such strong gravity, it's just pulling some of those pieces from its rings into the planet itself. And so eventually the ring system might disappear because all that material would have been dispersed, either fallen into Saturn or kicked out into space. But again, we don't fully understand the system of rings or why planets have rings or where they originated from. That's still stuff we're learning, and we're gathering information about the structure and nature of rings around planets. Do planetary rings always align with the parent planet's equator? I have not seen any evidence of a ring system that wouldn't align with the planet's equator. Because as the planet is rotating, that's where the rings are also orbiting around it. So it's following the same axis of rotation as the planet is how those rings are going around it. Once you get further out, well past the rings here, that's when you start to see moons not orbiting in the same equatorial plane as planets. But most moons even follow the same pattern as rings, where when they're closer enough to the planet, they will still orbit around the planet's equator. But then when you get further out, you get some of those captured asteroids around Jupiter and Saturn that have become moons, and that's when you'll start getting them kind of going north-south or any which way, because they're far enough out they can sustain stable orbits that are not in the same axis of rotation as the planet. Yep. How many moons can fit across Saturn? So the moon is 4 times smaller than the Earth. So if there was 21 Earths across Saturn here from one edge of the rings to the other edge, take 21 times by 4, and that's how many moons would fit across the face of Saturn here as we're looking at it. How thick is Saturn's atmosphere? Well, could be thought of as a trick question, because Saturn is a gas planet and it's all atmosphere as far as we know. We have no idea if there's anything near the core of Jupiter or Saturn or gas planets. We think there could be, but we haven't been able to detect that far into the atmospheres, where, as far as what we can tell, the whole entire planet is straight atmosphere. So the whole entire diameter would be Saturn's atmosphere. And you might think, well, if it's all atmosphere, it's all clouds and gas, can we just fly right through it? Well, it turns out that as we get into the clouds of Jupiter and Saturn, those clouds and the air pressure are so strong that if we were to fly through it, it would crush us like a pop can. Just the sheer air pressure. And this is not just a mathematical calculation. This is what happened to the Cassini spacecraft as it flew into Saturn when it was running out of fuel back in 2017. We also did this with the Galileo probe going into Jupiter, is that it got a few miles, about a mile or so below what we see as the surface of the planet before the temperature and air pressure crushed it and we stopped receiving signals from these spacecraft. So our gas giant planets, as far as we are able to detect, are just all gas. There is no rocky, hard surface that we are aware of. We think there could be, but we have no direct evidence to show that there is. So that'd be what's in the center of Saturn. As far as we can tell, just more gas. Although the exciting thing is that we think it's because of the temperature and pressure as we get below those cloud tops, that it's hydrogen, but in a liquid metallic state. And so that way it's squished so much that it's, instead of being a gas, it could act more like a liquid, and a liquid metal, so it can carry currents through it to create a magnetic field. And so that's one of the ways we're studying the inside of these gas giant planets like Jupiter and Saturn, is by studying their magnetic fields around them, because that tells us what's on the inside to create that magnetic field. Now, I do want to just pay attention to time. We are right about 9 o'clock, and it looks like Tad brought us back to a star cluster. So I'm willing to hang out. Tad, how long are you available to hang out for a little bit longer?
I'm willing for a little bit longer. I will say the clouds have come over. This is just a saved image of M13 at this point. I'm not even sure I'm seeing any stars. The moon is still there for a little bit. But yeah, I'm going to be here for a little while. I'm going to try out another camera here. And before anyone, I do want to make sure, by the way, I want to say a huge thank you to Darcy here. Here, Darcy, I'll send some light. That's Darcy. Sorry.
Thank you, Darcy.
Darcy's been our gopher tonight, no pun intended, and has been really great helping us out with the telescopes and moving everything around and definitely keeping track of all the cables and the wires and everything. So huge thank you to Darcy over here. And I believe they're going to go home and do a lot of homework. Is that correct, Darcy?
Yes.
Yes, I hear a definite yes for doing homework on a Friday night.
Well, just because we are at the end of the time we said we'd go to, I do want to thank you all for being here. And just know that our star parties and our astronomy programs are generously supported by funds from Ruth and John Huss and donations from visitors like you. So if you are willing and able and are interested in supporting the Bell, we have a link here that any gift of any size has a huge impact here on what we do at the museum to bring programs like this to you. It looks like we have plenty of questions that have come in through the program, and I know that we weren't able to get to them all, so I apologize for that. But we will be writing these questions down, and we'll do our best to post the answers to these questions when we post this video as well, because we have been recording. So thank you all for being here. I will hang out for a little bit longer if I see any more questions come through. I'll get to a few more of them as I can. But again, enjoy your evening, enjoy your weekend. Thank you so much for being with us on our very first virtual star party here from the observation deck at the Bell Museum. Thank you, everyone. Okay, let's see. So we have a few more questions coming here in. I'll just try to answer a few of them as I still see we have a few participants here on the webinar. But again, feel free, if you need to leave, we will post this recording after. Can stars be pink? And also, what are all the shapes of galaxies? So stars come in a range of colors. They can come in from cooler stars that we would see as red. As they get hotter, they'll go from red to orange to yellow, which are medium temperature average stars, all the way up to white and blue stars. So if you think of pink as kind of being a shade of red, I guess you could have a pink star. We usually just refer to that as red. And then what are the shapes of galaxies? Galaxies have three main categories for their shape. We have spiral galaxies like our own Milky Way galaxy and like the Andromeda Galaxy saw a little bit earlier. And then we have elliptical galaxies, which are kind of just blob shaped, where they're kind of ovals. So they don't have any defined spirals or anything like that, but they're just kind of these nice contained ovals. And then we have our third category, which is everything else. It's called the irregular galaxies. They don't have any defined shape. They're not even ovals. And so there's irregulars, whatever type of blobbish shape they happen to be in. So those are the three main categories of the shapes of galaxies. And there's lots of subcategories, like we here at the in Milky Way, we're not only a spiral galaxy, but we're called a barred spiral galaxy. So instead of just having a point in the middle that spiral arms come out from, we have a bar across it and the arms then come out of that. And so galaxy shapes, that's a whole branch of study on its own, because we're still figuring out how galaxies got such different shapes and what happens when two galaxies merge. What shape do they take then? And so it's really interesting. An interesting part of astronomy to study is the shape of galaxies and how do they get that shape. How big is the biggest star in our galaxy? The biggest star in our galaxy, I believe, is VY Canis Majoris. And so that one, is it Scuti? Now I'm getting my own facts mixed up here. They're quite large. They put the sun to shame. And so the sun is a gigantic star compared to us, and then the sun would look puny compared to these giant stars out there. There is a great YouTube video out there that I really like. It's Star Size Comparison HD, and that will give you a sense of how big things are and the scale of stars in our galaxy there. Okay. Thank you all for joining us. I see a few of you waving off, so I appreciate your time here this evening. And what are the names? There was back to the question about Jupiter, because we saw Jupiter for a little bit this evening. What are the names of the two moons of Jupiter that we were seeing? And so as they orbit around, I don't remember which one was which exactly as we saw it tonight, but the ones that's going to be closest to Jupiter in its orbit is Io, then it's Europa, Ganymede, and Callisto. Back to the idea of I eat green carrots. So I'd have to watch them over a course of a few nights to see which one is which, to see how their orbits go and when they turn from being kind of towards their outer part of Jupiter to crossing back in. Because when it looks like there's one just at the edge of Jupiter, like we saw tonight, that could be because it's just coming around on the backside of Jupiter, or it could be coming across the front of it and just looks close to it. So we can't quite get that full depth of its moons as we saw it in just one snapshot as we see it tonight. By tracking them over time, then you can start to get their orbital periods and then figure out which is which. Okay, I think I can hang on for a few more minutes, answer maybe 2 or 3 more questions. One of them I see coming in, do stars move in orbit like planets? Kind of. Planets are going to orbit a central object like the sun. They're going to orbit a very large, massive thing. Now, some stars can orbit each other. We call those binary systems, where we have 2 stars orbiting each other, much like if you're a Star Wars fan. In the movie, Tatooine has 2 suns coming up. Stars can orbit each other. Stars can also orbit black holes, which is a more massive object. And so as stars orbit more massive objects or orbit each other, that's how we can figure out how much mass they have, how big they are. And that's actually one of the ways we can find out where black holes are anyways, is by watching the stars we can see orbit around something that's invisible, that we can't see. And so stars can orbit like planets, but they can also move through space. Like our sun is not orbiting any other star or a black hole. So our whole solar system is just moving through the galaxy on its own. So stars can, but not always. They don't have to orbit like planets do. Okay. How old is the moon? So we saw the moon earlier today, or earlier tonight, both a live shot from our cameras on the roof deck, but then also a captured shot from just earlier this week. And so our moon is roughly the same age as the Earth, which is about 4.5 billion years old. And so we know that it's roughly the same age because it's made of a lot of the same materials. And we know that because astronauts were able to bring those back, and it's in labs, we can figure out which, if a rock originated at the Earth or if it originated on the moon. So the moon's roughly the same age as the Earth. And it looks like Tag got a live shot of the moon there as clouds are moving in front of it. So we can see that we are still battling some of those clouds to the south of us. Okay, if our sun was a blue star, would our sunlight be blue? Yes. And so there are stars out there. There's Kepler 47b that is orbiting, that's a planet that I believe is orbiting a red star. And so the idea is that instead of shining the white light that we see here and where plants would grow with chlorophyll to make them green, that the main wavelength of light coming off that star would affect how the organisms would evolve on that planet if that planet had organisms such as planets. The wavelengths of light coming from a parent star will affect the planets orbiting around it. Okay, looks like we have a lot of clouds coming in, kind of making that image a little blurry, but we can see some of those craters towards the bottom of that image here. And we'll do 2 more questions. Mark asked earlier, can you point to the dead star? The dead star that we looked at was the white dwarf inside the Ring Nebula, M57. So if you have your Bell Museum star map, that was M57, kind of right close to the center of your map. And so that was the white dwarf at the center of that Planetary Nebula. That was the death of a star much like our sun, where it's not too hot and not too big. Okay. Another great question here. I think I'm going to end on this one. It's from Colleen earlier. what happens if two stars mix together, because we just said that stars can orbit each other, and sometimes they can merge. So white dwarfs, which are dead stars, if it has a companion star, the white dwarf can actually suck material off of that companion star. And when it does that, it can make itself large. So that dead star, that core of the star that's already died, can actually kind of siphon off material from a companion star. And when it does that, it can actually supernova then. So a white dwarf that has already died from a star that would never have exploded on its own, by siphoning material off of a neighboring star that's orbiting it, could in turn, in fact, become a supernova. But we also have recently found that black holes, which are another form of a dead star, they can also merge. And we found that through gravitational waves. So the first detection of a gravitational wave came back in 2015, and we've been finding more and more of them. We found neutron stars merging. And so two, again, another type of a dead star colliding and smashing together, making other heavier elements on our periodic table like gold. And so stars can collide both when they're alive and living their normal lives and when they're dead via a white dwarf, siphon material off a companion star to supernova, or two neutron stars, or two black holes merging. So stars have such an interesting lifespan, and it's not, that lifespan doesn't end at the end of their fusion burning phases. They can do a lot of really cool, exciting things even after, when we call them dead stars. And so I'll put that on our list to find more of these dead stars in many of their different forms. And maybe we can talk about those next time in the upcoming star parties. Because again, it's one of my favorite topics to talk about is the lifespan of stars and how they can die and what that would be seen from here at Earth. So with that, we're just about at 9:15 here in the evening. Again, I want to thank you all so much for joining us this evening. I hope you had a good time. This is our first virtual star party and kickoff to what I hope is a great observing season here this fall and into the winter. Thank you, everyone. Thank you, Tad and Darcy up on the roof deck.
You're welcome. Have a great night, everyone. There's Darcy. Stay safe.